The nth order permutation matrix refers to an n by n matrix in which each column and row has exactly one and the rest of the components are 0. We need to find the exponential generation function for the number of symmetric nth order permutation matrices. Well, so here is matrix A, which is nth order permutation matrix. The series expansion of exponential function is given by e to the power of x equals 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial and so on. Same, this series also converges for square matrix A. So we can write down that e to the power of A equals identity matrix plus A over 1 factorial plus a squared over 2 factorial plus a cubed over 3 factorial, and so on. And I here is the identity matrix of the same order as A. So here matrix A is given. Let's try to find a squared. So a squared equals matrix A multiplied by matrix A. So it equals, let's see, so it's 1 times 1 plus 0 times 0 plus 0 times 0, so the first entry is 1. Then 1 times 0 plus 0 times 0 plus 0 times 1, so it's 0. Then 1 times 0 plus 0 times 1 plus 0 times 0 is also 0. Next row we get 0 times 1 plus 0 times 0 plus 1 times 0, so it's 0. 0 times 0 plus 0 times 0 plus 1 times 1, so here we have 1. Next we have 0 times 0 plus 0 times 1 plus 1 times 0, so it's 0. And the last row, the first entry is 0 times 1 plus 1 times 0 plus 0 times 0 is 0. 0 times 0 plus 1 times 0 plus 0 times 1 is 0. And 0 times 0 plus 1 times 1 plus 0 times 0, so it's 1. As you can see, a squared equals identity matrix. Well, now let's look at a cubed. So a cubed equals a squared times a. We know that a squared equals identity matrix, so we can substitute identity matrix for a squared. So it equals identity matrix times a. So it equals a. Now let's look at a to the fourth power. A to the fourth power equals a to the third power times a. A to the third power is a, so it's a times a. So it's a times a, so it's a squared, and we know that a squared equals identity matrix, so this equals identity matrix, and so on. So we get that the even power of a is identity matrix, while the odd power of a equals a itself. So we can write down that a to the power of k equals either identity matrix if k or k which are even, k is even, or it equals a for k which are odd. Then we can write the series expansion as e to the power of a times equals identity matrix plus a squared plus a over 1 factorial plus a squared over 2 factorial plus a cubed over 3 factorial, and so on. In our case it equals matrix where the first entry is 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on. The next entry is 0. Here we have 0. Here we also have 0. Here we have 1 plus 1 over 2 factorial plus 1 over 4 factorial, and so on. Here we have 1 over 1 factorial plus 1 over 3 factorial plus 1 over 5 factorial. So only odd numbers here, and here only even numbers. Here even numbers, here odd numbers. In the next row we have 0 again, then 1 over 1 factorial plus 1 over 3 factorial, again odd numbers, 1 over 5 factorial, and so on. And here again even numbers, 1 plus 1 over 2 factorial plus 1 over 4 factorial, and so on. So by series expansion we know that sin h of x equals e to the power of x minus e to the power of negative x over 2, which equals x plus x cubed over 3 factorial plus x to the 5th power over 5 factorial plus x to the 7th power over 7 factorial, and so on. While cosine h of x equals e to the power of x plus e to the power of negative x over 2. So this equals 1 plus x squared over 2 factorial plus x to the 4th power over 4 factorial plus x to the 6th power over 6 factorial, and so on. If we put x equals 0, or x equals 1, we get that e to the power of 1 equals e. So it equals 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so on. And we get that cosine h of 1 equals 1 plus 1 over 2 factorial plus 1 over 4 factorial, and so on. While sine h of 1 equals 1 plus 1 over 3 factorial plus 1 over 5 factorial, and so on. So we can express the required term as e to the power of a equals 1 plus e 0, 0, 0, cosine h of 1, sine h of 1, 0, sine h of 1, and cosine h of 1.